Okay, so we left off at this example, and this example said, draw the compounds. Draw these, please. The first one's 3-ethylpentane, and the second one's 2,2,4-trimethylpentane. Oh, we're testing our organic nomenclature, aren't we? Okay, so some people like these much, much better because there's hardly any choices and there's less decisions that you have to make. These names are basically your blueprint, and you need to build off of this blueprint. So let's tackle the first one, 3-ethylpentane. Pent, how many carbons does that represent? 5, right? 1, 2, 3, 4, 5. All right, so after I draw the 5 down, on the third carbon, I get an ethyl group. All right, so here's my first carbon, there's my second carbon, here's my third carbon, and my ethyl group is CH2, CH3, 2 carbons in total, right? So there we go. There's the structure. That's all that I need from you. Do you see how easy that was? There's 3-ethylpentane. Now, some people like to go through and they like to add in enough hydrogens to make these things work. And I do recommend that. So this is CH3. This carbon has 2 bonds, so it needs 2 more hydrogens. This carbon has 3 bonds, so it only needs 1 more hydrogen. This carbon has 2 bonds, so it needs 2 more hydrogens. And this carbon has 1 bond, so it needs 3 more. So there is the more full-bodied approach to the structure, and that is what I recommend from you. So don't just write down the carbons. I do that sometimes as shortcuts to give you examples, so I'm not here forever and ever and ever doing these. But you got to keep in mind those hydrogens are present. So sometimes we take those for granted, and we shouldn't. Next one. 2,2,4-trimethylpentane. Pent, again, means 5. 1, 2, 3, 4, and 5. All right, so on carbon number 2, so that could be that one, right, if I number from left to right. And on carbon number 2, well, if I draw one up, I'm going to draw one down just to get them far apart. They don't squish up my structure. I get a methyl-methyl group, right? Trimethyl. That means there's 3 of these methyl groups. Where are those 3? On carbon 2, on carbon 2, and on carbon 4. That's where those are going to be located. A methyl group is 1 carbon, right? So CH3, CH3, and CH3. Now I can go through and just fill in my hydrogens if that's what I want to do. This carbon has 1 bond, so it needs 3 more hydrogens. This one has 4. It doesn't need any. This carbon has 2, so it needs 2 more hydrogens. This carbon has 3 bonds, so it needs 1 hydrogen. And then this carbon here on the end has 1, so it needs 3 more. So I can go through and write in the other hydrogens. It looks a little dirty and nasty. I can clean this up a little bit if I want. I can rewrite it and just not draw the bonds. So in the main chain. So here's CH3. There's a carbon with a methyl down and a methyl up. And then CH2, CH with a methyl up, and then CH3. So if you want to clean it up, you're more than welcome to do that. And that's what that would look like. All right. So there's 2 more examples going from a name to a structure. And again, I think people respond to this a little bit better than the other way. All right? Okay, now we're not done. So what we need to focus on now is I told you that these snake-like structures can be straight across, right? We have a head and we have a tail. And that's what we've been naming. That's what we've been drawing up to this point. But I also said that the structures can circle around on themselves and the head can bite the tail. And we get a ring. And that ring is cyclic. And this is what we call cycloalkanes. Okay, good news for you is that the rules don't really change any. The rules stay the same. Everything that we've talked about so far, nothing gets modified except we add something in. And what do we add? We add the word cyclo into the name to let you know that this is a ring structure. So anytime you see this prefix in front of a name, note that that means the structure is circling on itself to form a ring. And we have now denoted that in the name that we are providing you. And one of the things you got to remember about cycloalkanes is that their general template is a little bit different than alkanes. So with alkanes, we saw CnH2n plus 2. Well, for cycloalkanes, because the head and the tail circle around and meet, we need to remove some hydrogens in order to allow that connection to take place. So with cycloalkanes, we actually see CnH2n. We leave off those two. So one bond gets removed from the head, one bond gets removed from the tail or atom, and then that creates an opportunity for the two to hook back up. So that is the general template for a cycloalkane, and we need to add that into our toolbox. So it's going to be common now for these questions to say, hey, here is, a number of carbons and here is a number of hydrogens. Based on this, is the structure an alkane, or is the structure a cycloalkane, or is it neither? It might not be neither one of them, right? So there's other possibilities that are out there for this to happen. Okay, so another thing, cycloalkanes are very often written as skeletal structures. And skeletal structures are basically no carbons, no hydrogens, nothing. Just a bunch of zigzaggedy little lines, because it really cleans up the structures for us and it allows us to draw it a little bit better. Okay, so rules for the cycloalkanes. Very similar to the straight chain alkanes. There's hardly anything that's different. You still have to find the parent hydrocarbon. And that parent hydrocarbon is the longest carbon chain. And this could be the cyclo group, or it might not be the cyclo group, right? That just really depends on the structure. So there's going to be moments where the structure that's drawn as a circle will be classified as the parent chain, and we will name it as such. And then other times, the circled structure will be a substituent, and that will be attached to a really longer part of a molecule. And then we handle that a little bit different, okay? So if the cyclo group is attached to the really long alkane, then this cyclo unit is still going to be called a cyclo unit, no matter how that goes. But again, we just change the ane to a YL. So cyclopentyl and cyclopentane. One is basically, it's the longest chain. The other one is a substituent name. All right, so let's take a look at some examples. What we see on the left-hand side is cyclopropane. So 1 carbon, 2 carbon, 3 carbons. We did not draw it in a skeletal structure here. All the carbons and hydrogens are represented, and it forms a circle. So carbon connects to a carbon, which circles back around and connects to the first carbon. That is why we call it a cyclo unit. Okay. If you did not want to draw all of the hydrogens and carbons, you would simply draw a triangle, and that represents cycloprotane. It's as easy as that. All right. Cyclobutane's the same way. This is 4 carbons in total that are in a ring, and here they've drawn all of the carbons and hydrogens for you. If you did not want to do that, though, you could simply just draw a box, and that represents cyclobutane. So this understood to be a carbon, that's a carbon, this one's a carbon. And there's enough hydrogens to make those suitable and happy. Okay. Same thing with cyclobutane. There's a carbon, there's a carbon, there's a carbon, and there's a carbon. And there's enough hydrogens on them to make them all happy. You're going to see me draw these dots like this. It keeps me straight, kind of my mind thinking on the right track. So that way, when I do get more complicated examples, I can quickly count my dots that I have drawn here, and each one represents a carbon. So you'll see why I do this a little bit later on, but that is something that I do tend to do. Cyclopentane, again, all carbons all the way around, hydrogens connected to them all the way around. But if I wanted to draw a circle, so there's my first carbon, here's my second carbon, there's my third carbon, here's my fourth carbon, There's my 5th carbon, and I need to now connect it all the way around. So there is cyclopentane. Cyclohexane gets a little bit bigger, so 6 carbons in total. There's my first one, there's my second, there's my third. I draw straight down for 4th, straight down for 5th, and then I come to the center for the 6th one. So this is my cyclohexane structure right there. Again, 6 carbons, all connected together in a circular fashion all the way across. So there's maybe a little bit better drawing of what I just did, and this is what you're going to start seeing in your textbook, and this is what you're going to start seeing in Blackboard and maybe on even tests and exams and so forth. We don't have to just draw skeletal structures for cyclo units. We can also draw skeletal structures for normal compounds as well. Again, a very shorthanded notation in order to do this, and this is why we do it. We don't want to take the time to write down the carbons and the hydrogens. You know, if we're talking to other people that are well-versed in organic, then we can make assumptions, and those assumptions are we know that they know a few basics, and one of those basics is that at every single one, there's 1 carbon, there's 2 carbons, there's 3 carbons, there's 4 carbons. Those are carbons, and there's enough hydrogen that's there to satisfy those carbons. So this is the skeletal structure of butane. This is the skeletal structure of 2-methylhexane. So number 1, number 2, number 3, number 4, number 5, and number 6. That's why this is a hex. The 2-methyl, because on the 2nd carbon, there's a stick that's drawn out, and that bond, basically, it looks like it goes to nothing. But on the end of this, it's understood to be a carbon. So that 1 carbon is classified as a methyl group. Here we have 6-methyl, 2,3-dimethylnonane. All right, so where is the longest carbon structure? If I just kind of start across, all the way across, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's where the nonane comes from. And then on carbon 2 and carbon 3, I have dimethyls. So there's a methyl group on each one of those numbers. So here's a methyl group on carbon 2. There's a methyl group on carbon 3. And then finally on 6, 1, 2, 3, 4, 5, and 6, I have an ethyl group. So here is 1 carbon and there is 2 carbons. So this is a substituent that's attached to a long chain. That's a substituent on a long chain. This is a substituent on a long chain, and that's where that name comes from. All right, so there is a little bit of intro on skeletal structures and really how we can utilize them for both the cyclo groups as well as the straight chain groups as well. All right, so let's kind of go through and take a look at some structures and just begin to name them. The first one on the top, we've seen this one before already. There's a total of 3 carbons here, right? 1, 2, and 3, and they're all in a ring. So 3 carbons is going to be called a prop, and this is an ane because it's all single bonds all the way around, and it connects in a circle. So this is going to be a cyclo in front, so cyclopropane. All right, we take a look at the example down below. This again is a circular structure, and that is my longest carbon chain in that circle. So 1, 2, 3, 4, 5, and 6. There's 6 carbons all the way around here. So this is a hex, and it's an ane because it's all single bonds all the way around. And this is the main chain, right? So there is my main chain, and this is a substituent that's hanging off. That substituent is a 1 carbon, and that is going to be called a methyl. And then I've got to kind of bring into the picture this word cyclo, because at some point in time, I have to tell you what this is basically going to be a ring and how it's going to be called a ring. So the way that I do that is I kind of squeeze it here in the middle, because the cyclo goes with the hexane part. It does not go with the methyl part. So the hexane is the part in the ring. So this is going to be called a methyl cyclohexane. Again, the name of the game, give your substituents the lowest group number possible. So because this is a ring structure, I could start this anywhere, and I'm going to start the carbon at number 1 here, because that is where my only group in this structure is going to be attached to. So I give that the lowest number, and that lowest number is a 1. All right, here's another structure. Again, rings do not have to be the longest chain. And here we see a 1, 2, 3, 4, a 4-carbon grouping system that's in a circle. And then here I see a chain 1, 2, 3, 4, 5, and 6. I don't go 7 because this is really part of that ring, right? So 1, 2, 3, 4, 5, 6. This is a 6-carbon chain or a 4-carbon chain. 6-carbon chain is the longest, so therefore this is the parent chain. That's what we would call that. So 1, 2, 3, 4, 5, 6. This is a hex. It is an ane with an A-N-E ending, so hexane. And then on carbon number 1, I have this circle structure. And this is a cyclobutyl group. So cyclobutyl hexane. I can put a 1 here in front if I want to. I don't have to. It's understood to be there. If I don't draw it, it's understood to be there. Only if there's one group and only if it is in the first position do I not have to write down that number. But I'm going to actually recommend you write down that number every single time just to be safe, so that way you don't miss any points out. Okay? So 1 cyclobutyl hexane is going to be the name of this structure. Once again, the cyclobutyl, it is a larger piece, but it's not the major chain. There's more carbons that are associated there, and those carbons are a total of 6, not 4. All right? Okay, so let's take a look at another example. Here we go. Let's name it. Looks like a lot. I'm going to simplify this down a little bit, though. Right? There's a lot of carbons and hydrogens here. This looks like a 6-membered ring right there. So I'll draw a 6-membered ring like this. And then off of this carbon, we have a little jagged piece that represents 2 carbons. And then here we have 1, and that represents 1 carbon. So we need to name it. I'll find my longest carbon chain. My longest carbon chain is actually this 6-membered ring right there. 6 carbons in total all the way around. So this is a cyclohexane. Again, cyclo because it's a ring. Hex because there's 6 carbons in total. Ane because they're all single bonds. All right, so now I got to figure out, well, what goes where, right? I mean, what goes where? We have this ethyl group on the top and we have this methyl group on the bottom. So this piece, 2 carbons, that is your ethyl group. And then this piece, that is your methyl group. Well, this ring system allows me to number wherever I need to number. And quite honestly, E comes before M. So my choices are really to give this a 1 and this a 2, or this a 1 and this a 2, right? That's my really only 2 options that I have here. Because E comes before M, we probably would like to give this a lower number. You know, we look at these 2 groups and we don't pick one over the other. They're pretty much equal. This is an alkyl group and this is an alkyl group. It's all carbon, hydrocarbon based. So no differences in preference. But because E comes before M, we probably would like to give this a 1 and give this one a 2. So in the naming, this is going to be 1 ethyl, 2 methyl, cyclohexane. And that's why we do that. If you gave it to me a different way, and if you did number backward, and you gave me 1 methyl, 2 ethyl, I would probably still give you at least partial credit for that, if not full credit for that, because all the pieces and parts are there for you and you are recognizing them and you're putting them together. You just made a simple mistake. That's all that you did. All right. A couple more examples are here. So we'll go through and quickly name these as well to give you some more practice. Here we got a ring structure that is the longest chain. That's the majority of the structure there. So this is a cyclopropane because there's 3 carbons in a ring. And then on carbon number 1, this here, we have a 1 carbon group. And this is called a methyl group. So methyl cyclopropane, or if you wanted to, you could draw the 1 in front and give it a actual concrete number that's understood to be there. Next one over, longest carbon chain. It is the ring here that's the majority of the structure. No way that you can beat 6 carbons in a row. So this is a cyclohexane. And then on this carbon, and because we can start the numbering anywhere where we need to, and because there's only the groups here on that carbon, that needs to be carbon number 1, we have a group that's a methyl to the left and a methyl to the right. That's understood to be 1 carbon. So there's 2 methyl groups. So this is a dimethyl, and I have to give each one of them a number. So 1,1-dimethyl cyclohexane. Down here at the bottom, we see this cyclopentane ring. That is my longest chain right there. There's no way I can beat that out. So cyclopentane. And I need to figure out how to number. Well, my options are 1 and 2 or 1 and 2. It really doesn't matter which way you do it. You're going to get the same answer no matter what. And the reason is because this is a 1 carbon and this is a 1 carbon. So these 2 groups are both methyl groups. So this is a dimethyl, and you're going to get a 1,2 no matter how you do it. So 1,2-dimethyl cyclopentane is going to be the answer to the name for that particular compound. All right, next one over. Again, longest carbon chain, and we can beat the ring out this time. So this ring is 3 carbons in total, 1, 2, and 3. However, my longest chain could actually be 1, 2, 3, 4, and 5, can it? So this is my longest carbon chain right here. So 5 carbons in total. 5 carbons in total is going to be a pentane. They're all single bonds all the way across. Which way do I number? Doesn't really matter. The reason, 1, 2, 3, 4, and 5. Or if you go the other way, 1, 2, 3, 4, 5, you'll also get a 3. You'll get a 3 no matter which way you go. So this is going to be a 3, and this is a cyclo. It's still a cyclo. It's still a propyl group because there's 3 carbons that are present. So this is a 3-cyclopropyl pentane. And that's going to be the IUPAC name or systematic name for these compounds. And that's what we've done. In all of these examples so far, we've given systematic names or IUPAC names based on the rules that they have given me. We've never really addressed common names that much at all, period, at all. And the reason is because I told you that we try to stay away from those common names whenever possible. There's a few times that we need to do it, and we will see those, and we will start working with more examples of those. But these are truly IUPAC names that follow the rules that are guided to us by the International Union of Pure and Applied Chemistry and all of those PhDs that make that decision. Give me a break.